journey into the solar system and beyond on our astronomy course. We're now looking at Gravity and Orbits, SP7b. So hopefully this will be a useful session for you to do. You can pause the video, have a look at other things, write down some answers because you need something to write with as well. So let's move on with this. The builders are next door, so there might be some banging and knocking, but hey ho, we'll have to cope with that one. Okay, let's move on then. So straight away into a starter really. Gravity and Orbits is what we're about, and there's a animation there of various orbits and the Earth at the centre and an illustration of a satellite. But first of all, you know, we know about satellites, I would think, so make yourself a list, pause the video, make a list of what satellites can be used for, and then beyond that is like, what are the requirements for these different uses? So pause the video and see what you can do with those. Okay, hopefully you've got a list of things there, and if you're feeling really ambitious, you've thought about the challenge and say, what do these different uses of satellites require? And hopefully you've got the following sort of areas there, in that we can use satellites for TV broadcasting. Many of you might have Sky TV with a dish on the side of your house. Communications, obviously, if you ring someone in the United States, that phone call is likely to go via satellites. Ditto Australia and all that. Weather and meteorology, you'll see that on the news, weather forecasts on television, you know, every day. Looking at the weather forecasting using that, and meteorology predicting weather. Navigation, of course, sat-nav systems. You've probably got one on your phone that can do that with Google Maps and such like, and cars have it. Mapping and remote sensing. The geographers amongst you may have come across some remote sensing, but you'll certainly should have seen images where different crop distributions and things like that. Obviously observing space and other bodies. The Hubble Space Telescope is an example of that being there, and also the International Space Station, which you'll be aware of, is up there in orbit as well as a satellite. A satellite is something that orbits another body out in space, whether it's natural or artificial. Military observations and espionage, spy satellites, you've seen them, I'm sure, on TV films and series for that as well. And also search and rescue, trying to locate somebody who's in difficulty in the middle of an ocean, and then the satellites are going to be useful for finding that as well. And some things have beacons that actually will send off pings to identify where they are if they get into distress. For the challenge question, what will these satellites require? Well, if you want a satellite broadcasting TV image, then it's got to stay in the same place in the sky relative to the viewers. It's no good if your Sky TV only works while a satellite's passing and then it goes off. It needs to be pretty constant above that place on the Earth. And also for mapping ice at the poles, North Pole and South Pole, with global warming, of course, that needs to pass over the poles periodically to see what's happening in there, and it can't sit over both of them. So it has to pass over them. So there are different uses, as we'll see as we go through this lesson on this. Okay, so let's carry on with this one. Objectives-wise, learning-wise, we're going to see how the speed of an orbiting body affects the radius of its orbit, and explain how the radius is affected by the speed. We are looking back to centripetal force and circular motion. In this, describe the orbits of moons, planets, comets, artificial satellites, and explains why the velocity. Again, in the previous bullet point it says speed, but this is now velocity. We need to remember the difference. How the velocity of a planet changes even if orbiting at steady speed. And then recall the factors that affect the strength of the gravitational field. And I'll get myself out of the way. Factors that affect the strength of the gravitational field, and explain why G, lowercase g, has a different value in different bodies in the solar system. So that's what we're about to try and find out during this session. And there'll be various things for you to pause, stop and think and do. I'm back now, so let's have a look at our next area. Okay, how do planets orbit the Sun? Planets, as we should know from our previous lesson, they travel in elliptical orbits. That's not perfectly circular, slightly squashed circular, and that's held in orbit by the force of gravity, which I'm sure is not too radical for us. The pull of gravity causes the planets to speed up when they move towards the Sun and slow down when they move away from it. Clearly, if these things are working in elliptical orbits, they're not a constant radius away from the Sun, and therefore at some stage they will be relatively moving towards, and at some stage they will be relatively moving away from the Sun. And the changing speeds of the planets as they orbit the Sun make it difficult for the orbits to form a perfect circle, hence the elliptical orbits as well. All the planets in the solar system orbit in the same plane. That means they're all in this flat area. Okay, they're not coming across, they're all pretty much in the same plane, on the same sort of flat surface you might think about. They all orbit like that, as you can see. So they all orbit in what's called the same plane, or they are co-planar. as it sometimes is described as. Comets then. Comets are also satellites because they orbit the sun, but most planets travel around the sun in planets are in slightly elliptical orbits, but comets have very, very elliptical orbits. And for most of its orbit, a comet is a long way from the sun, and it only sort of comes close enough for the Earth to observe it every certain number of years, as we'll see later. But for most of the orbit, it's a long way away from it. And you can see that comet there, Comet Hale-Bopp. You heard of Halley's Comet, but that's Comet Hale-Bopp taken, and it looks like, that's the classic image of a comet. And it looks like the comet is streaming downwards in this, because it looks like this is the head of the comet and the tail of the comet is reflecting its direction. But that's not quite the case, as we shall see. Okay, so when you think about what a comet is made of, and we need ice and dust, why does the tail only appear when the comet's orbit takes it nearest the sun? Because the comet's tail consists of water and gas and dust that evaporates from the sun's heat. So obviously when it's close to the sun, that is happening in there, and you're getting that tail generated as well. But comets, why does it face away from the sun? Well, as you can see on this diagram here, we've got the sun in the centre, and the tail of the comet actually faces away from the sun. And as you can see here, there's ion tails and dust tails, and they're not quite the same thing. But as you'll notice, the ion tail always faces exactly away from the sun. And if we've learned anything about the sun, or know anything about the sun, we should know a little bit about it and maybe explain how the ions, the charged particles from the comet, are moved away in the tail here. Okay, because this is the dust, but the ion tail is due to that one. And there is a thing called the solar wind. Okay, now obviously there are no particles in space, but the sun emits electromagnetic radiation from it, which of course will affect any other charged particles around it, because that's what electromagnetic radiation does. So this discharge from the sun, the charged particle discharging the electromagnetic radiation from the sun, will affect the charged particle. So there's ions coming out of the comet, then this solar wind moving away from the sun, it's emitted from the sun, will actually affect those charged particles and cause them to move away from the sun as well. So that's why comets actually the comet tail faces away from the sun, and it's not a sense of movement on this. When we get to sort of grown-up physics, which is not GCSE, but beyond that, we measure things in astronomical units, or AUs, as you will if you do A-level physics. And these comet ion tails have been observed to extend a great distance away from the comet as well. So, as you can see, this comet orbiting its very, very elliptical orbit, and freeze framing at various different points, you can see, the Earth's orbit is relatively circular, but the comet's orbit is much more elliptical, and you can see that the comet tail moves away from that. Pause the video if you need to have a look at that, but that's what happens for this. There's a more detailed diagram of it, which I've paused for you, showing the ion tail, dust tails, and we talked about those questions previously. But if we think about how these things are moving in orbits, we need to bring together our knowledge and understanding from earlier work we did this year about circular motion. We know about gravity being an attractive force, and we know that satellites are in orbit, and we know about circular motion. So I would hope that if we really thought about it, we can say, okay, I can see how these things link together, and we can start to get some understanding and draw things together. Because what we need to be able to do is, can we work out the relationship between the force of gravity and the distance from the centre of the Earth? Okay, the centre of the Earth, not the surface, but the centre of the Earth. And following that, I'll move myself off the screen here so you can actually see what's going on the slide. Following that, we can work out the relationship between the satellite's height above the orbit of the Earth and their speed at which they're going around the Earth. And again, we've got speed and not velocity, because that's important, and it's important for circular motion. So let's see if we can put together some things to think about these and understand why things orbit and put it all together. So to recap circular motion, we need to think of the following. Why does circular motion need a force? What's that force called? And there are three variables that affect the size of the force needed to keep an object moving in a circle. Think of the hammer thrower that we used in the lesson, and there's a graphic of her doing her stuff with a hammer at the moment in some sort of athletic competition. So can we put all those together, those 3 bullet points? Can we explain why those things work, and therefore how we can actually bring circular motion to explain gravity? Because she's basically twisting a hammer around, which is like a satellite or in orbit, applying a force, and then the force, she's turning off the force, and the thing's flying off. Okay, so can we put that all together? Pause the video and see if you can jot down the answers to those bullet points. Okay. Okay, then we're ready. Here we go. There's a bigger picture of somebody spinning round. And again, you can see the hammer as a satellite in orbit. And it's in orbit, and it's in orbit, and it's in orbit. Speed is increasing and increasing and increasing, increasing, increasing. And the gravity's turned off. And off the satellite goes. Obviously, you can't turn gravity off because it's due to the mass of the planet. But you get the picture, I hope. So, to recap, what did you put for these? Why does circular motion need a force? Well, the answers being, as I hope you put, the direction is changing, isn't it? It's moving in a circle, so the direction is constantly changing. And as we know that velocity is a vector, so the velocity is changing. And if we change a velocity, Isaac Newton said you need a force to change the velocity. So we need a force if it's going to keep moving in a circle, because direction is changing, velocity is changing. The force is called, which I gave away in the start of the lesson, it's called centripetal force, and it acts inwards. And the three variables that affect the size of the force and needed to keep an object moving in a circle are the following: the mass of the object, the speed at which the object is travelling, and the radius of the circle, or the radius of its orbit. Okay, so we need to know that, and we need to bring that with us from earlier work in year 10. So you need to know that. If you didn't, please go back and dig that out, because it is important for the rest of what we do in this module, okay, in this particular lesson. Okay, but that's important stuff. So we think about in gravity, what affects the size of an object's gravitational force? And, you know, hence why is the moon's gravitational force less than the Earth? It's about 1/6. How might the force change the further away you go from the centre of an object? Okay, most of these are spherical, we can assume that they are. And how will the gravitational force change if you move away from the surface of the object? And from that, could you plot or sketch a graph to show how the force versus distance would change for this, like this? So if we take an example, and you perhaps sketch this down on a piece of paper somewhere, and we have the blue circle represents the Earth, and we start our graph from the centre of the Earth. So this is the centre of the Earth, the inner core, right in the middle of it, and we move outwards to the surface of the Earth. So there's the surface of the Earth where we're all habiting, and then we move away further and further into space. So that's the x-axis on the graph. If we then, the builders are having a great fun next door, aren't they? Gravitational field strength from the centre of the Earth, so there's nothing below us because we're actually at the centre, theoretically, and as we move stronger and stronger and stronger up the y-axis, the gravitational force gets stronger and stronger and stronger. Okay, so if you're feeling up for a challenge, you could try and sketch what you think the Earth's gravitational field would do with distance. Okay, so if you're up for the challenge, you can do that now. If not, we'll come back to that later. But that's what we need to be thinking about. And if we can explain that, we're doing really, really well with our understanding. So, how does the gravitational field strength change with distance from the centre of the Earth and then from the Earth's surface as we go into space? Now, for your notes, you kind of need to be able to summarise what we've done so far with these and filling in these missing words. Okay, so and think about your circular motion knowledge and see if you can write those down. So for your notes, what you could do with doing is writing those sentences out and finishing them off. Okay, so pause the video, write those down. You can pencil in the answers if you're not confident, but hopefully if you thought about it, you should be okay. So pause the video, have a go with those, and we'll come back and talk about what the answers are and move on. Okay, so, oops. The satellite is held in orbit by gravity. This is required because, as we said, the object's moving in a circular motion. Circular motion, changing velocity is acceleration, acceleration is force. If gravity was turned off, not that you can, what would happen to the satellite? Well, as Isaac Newton said, it would continue in its state of rest or uniform motion. It would just move off in a straight line as the hammer does in athletics. When you let go of the hammer, it flies off. So when there's no force, the object continues in its state of uniform motion, as Isaac Newton said. I think it was his first law. The further away the satellite is from the Earth's surface, the smaller the force of gravity because it's far away. And satellites in near orbits, so close to the Earth, where the gravitational force is stronger, do they need to move faster or slower than satellites in far orbits? And why would that be? And the answer should be they need to move faster because the force of gravity is stronger, and if they didn't move fast, they would get pulled in towards the Earth's surface. as we'll see later in the lesson. Okay, so what do you know about gravity? Now, if you get more advanced gravity, you get the idea of, gravity waves and the effect of gravity around it in space, and you get diagrams like that, but probably not going to be reproduced in your exam question for this one. But we should know already that the weight of an object is equal to its mass times the gravitational field, because weight is a force measured in newtons, mass is how much of the object there is measured in kilograms, and obviously the force is depending on the gravitational field strength of wherever it is, the Earth's surface, Mars, the moon, wherever. Okay, so we should know that already about weight is mass times gravitational field strength. On Earth, the gravitation is 9.81 newtons per kilogram, often used as 10, but in an exam question they tell you what value they wanted you to use. So G is 9.81 newtons per kilogram, or can be often round up to 10, but take care of what it says in the question as what they wanted to use. And the gravitational field's strength on the surface depends on the mass of the body and its radius, i.e. from the centre of this sphere to its surface. So that's what it depends on in terms of the gravity. And we're obviously sitting on the Earth's surface experiencing gravity because we're away from the centre, and all of the mass of the Earth is below our feet. So that's where the most gravity is, at the surface, because all of the mass of the Earth is beneath us, none is above. Okay, as we shall see. So the greater mass and smaller radius gives a greater surface gravity. So the more dense something is, the greater the gravity is on it. And some of the outer planets have got horrendously large gravitational field strengths because they're so big and heavy. Very high gravity that we just crush anything that landed on there. So the force of gravitation between the masses, so you've got two masses, the moon and the Earth, they've both got mass, so they've both got gravitational forces that are attractive forces pulling in, depends on the mass of the two objects and how far apart they are. Okay, so hopefully that sort of makes some physics sense. To go back to our diagram then of planet Earth from the centre and move from the centre of the Earth outwards, I would hope, as smart people, we've thought, okay, the gravitational field strength will increase because the further we get from the centre, the more of the gravitation of the Earth's mass, is below us. So it will increase and it will increase and it will increase to a maximum when we're at the Earth's surface. There. So by the time we move out from the centre of the Earth to the surface, the gravitational field strength is at its maximum value, which we know to be 9.81 newtons per kilogram. Okay, so we can show that diagrammatically. This does make the assumption that the Earth is uniform density and it's all the sort of same mass per unit volume underneath it. But if we do assume that, and it is physics, we make lots of assumptions, then we see that to the Earth's surface from the centre, the gravitational field strength increases uniformly to a maximum of 9.81. Okay, because here we are at the surface of the Earth there. Okay, but the next step is what happens as we move away from the Earth's surface. Okay, so we're moving further and further away from the Earth's surface, from the sort of the mass that causes the gravitational field strength. And what would happen then is we get this type of arrangement, that from the Earth's surface, as we go into space, the actual gravitational field strength decreases, and the further and further away you go from the Earth's surface, the less and less gravity there is from the Earth, until eventually you get to the point where you're completely out of the influence of the Earth's gravitational field, and you're just in space where nothing's going to pull you towards it. Okay, so that should be a graph. Hopefully some of you sketched that out and got the idea of that already. And can you sketch it and explain it? It pretty extension for GCSE this, but if that works for you, makes sense, then you're doing well for this. So can you sketch and explain it? And how would that relate to satellite orbits? Because all the satellite orbits are obviously actually above the Earth's surface, aren't they? So all the satellites are from this vertical dashed line out here somewhere. And if you think about this, the further out the satellite is, the further out, the further out, the further out, the further out, the less gravitational field strength is going to affect it. And that's going to link to how fast it travels. Because if it's close, it's got a lot of gravitational field strength pulling it in. And if it's further away, it hasn't got as much. So if we can use that as ideas, we can perhaps start thinking about satellite speed of orbits and such like. If we link that diagram to this next one, so there's the Earth's and the gravitational field strength, whoops, and we actually then look at this diagram from the centre of the Earth. So we've got the same diagram here as the Earth's centre. We've got a satellite in a near orbit with a big arrow pointing towards the surface of the Earth, and a satellite in a further away orbit with a smaller arrow pulling it towards the Earth. And as what we can see here, as hopefully we saw right on this graph and this diagram here, is that the closer you are to the Earth's surface, the stronger the gravitational field strength is. The further away, the less gravitational field strength is. And that's what we show on this diagram here, where we've got a smaller arrow for satellites in far orbit, and satellites in near orbit need to have or have experienced a larger gravitational force, and that then impacts on the speed of their orbit of the Earth, because if it's got a high gravitational field strength, it's going to be likely to pull towards the Earth, so it's going to move pretty quickly to maintain its orbit, whereas things further away can actually move more slowly. If you're feeling really advanced, and again, if you're not feeling advanced, just move, just let this slide go. But these are the effects that we notice in terms of distance and mass, okay, between these. So the force to masses, if we have a bigger mass, double the mass here, the force increases there. But the distance, if we have a distance and we double the distance, we have a quarter of the mass. So we're talking effectively inverse square. It's inversely proportional to what happens here. It's advanced stuff. So the force of gravity is directly proportional to the product multiplied of the two masses. So you have two masses multiplied together. And the force is inversely proportional to the square of the distance. Now I think Miss Young said that you were doing inverse square laws in biology, to which I replied I knew we were going to colour them in. But so the force of gravitational attraction is inversely proportional to the square. So it's the inverse square law for gravity as you move away from the Earth's surface. And again, pretty advanced that. Top end GCSE only. Don't be frightened by it. And if you're feeling bold, I've got a couple of things at the end for you about that one. Here we have something nearly back to Earth, but certainly back to the visuals and not maths, is the idea of a comet orbiting this and the Earth's orbit there, the circular, slightly elliptical, and the highly elliptical orbit. So hopefully I'm just going to look at a video now, if all the technology works here, and we'll look at a video showing this in action and have a bit of a break. Okay, and clearly the video has decided not to play, so it's kicked me out of Active Learn, so you have to bear with me and I'll pause the video. We might have to return in part 2.